In mathematics, groups and coding theory is a very important topic. So today we start with the some topics from groups and coding theory. Now the first unit is integers. Now equivalence relation is nothing but a relation which is reflexive, symmetric and transitive relation on that set that we have seen already. Now see what is the meaning of equivalence class. When R is an equivalence relation on a set A, it is customary to write A, R, B instead of ordered pair A, B belonging to R. Also, since an equivalence relation is just a generalization of equality, we can write the symbols such as this one or this one or this one to denote the equivalence relation. Now, if this relation is an equivalence relation on a set A and A is a member of A, then the set equivalence class of A, it contains element X in A such that X is related to A. So this is called as the equivalence class of the set A containing A. So what is basically an equivalence class? Whenever some relation is an equivalence relation on set A, then for every element A from that set A, we can define equivalence class. So equivalence class of A contains all those elements X in A which are related to A. Now definitely this set is non-empty, as for every element A in A is related to A because the relation is reflexive. So every equivalence class is non-empty. Now see this example. Now see A equal to 1, 2, 3. R is equal to 1, 1, 2, 2, 3, 3, 1, 2, 2, 1. This is an equivalence relation on A. Now for every element of A, we decide the equivalence class. Now equivalence class of 1. Now by definition it contains X in A such that X is related to 1. Now by observing the pairs, here 1 is related to 1 and 2 is related to 1. So the elements 1 and 2 from A are related to 1. So what is equivalence class of 1? It is 1, 2. Similar way, what is equivalence class of 2? By definition, it contains X in A such that X is related to 2. So here 2 is related to 2 and 1 is related to 2. So again 2 and 1 means 1 and 2 are members of equivalence class of 2. Now equivalence class of 3. So it contains X in A such that X is related to 3. Now see which members of A are related to 3. It means 3 must be second element of every pair. So here 3 is related to 3. So no other element of A is related to 3. So equivalence class of 3 contains only element 3. So in this way, for every element of that set, we can decide its equivalence classes. Now here if you observe, equivalence class of 1 and equivalence class of 2 are identical. That means they are exactly same. And equivalence class of 1 and equivalence class of 3 are disjoint, means they do not have any element common. Same way, equivalence class of 2 and equivalence class of 3, again they are disjoint. Now see one example. Let Z be the set of integers and N be a positive integer. If A, B belong to Z, define A related to B if A is congruent to B modulo N. That is, if N divides A minus B. So that this relation is an equivalence relation on Z. Determine the equivalence classes of Z. Now here first we have to show that the relation is an equivalence relation on Z. It means we have to show that it is reflexive, symmetric and transitive. So in all we require three elements of Z to prove these three properties. So let A, B, C belong to Z. Now first is reflexive. So we have to show that every element A in Z is related to itself. Now by definition, A will be related to A if A is congruent to A modulo N. That means N divides A minus A. Now N is a natural number. So N divides 0. That means N divides A minus A. So by definition of congruence, we get A is congruent to A modulo N. So by definition of relation, A is related to A, and this is true for all A belonging to Z. Hence, relation is reflexive. Now, second property is symmetry. Now, in symmetry, for two elements A and B in Z, we assume that A is related to B. In that case, we have to show B related to A. Now, as A is related to B, by definition, A is congruent to B modulo N. So again, by definition of congruence, this implies N divides A minus B. Now, by definition of divisibility, N divides A minus B implies A minus B is equal to N into K for some K belonging to Z. Now, from A related to B, we have to show B related to A. That means B is congruent to A modulo N. So, we consider B minus A. So, it is minus of A minus B, which is equal to minus of Nk. So, it is equal to N into minus K. As K is an integer, minus K is again an integer, so it is L. So finally we get B minus A is equal to N into L. Implies N divides B minus A by definition of divisibility. Again, by definition of congruence, N divides B minus A means B congruent to A modulo N. So by using the definition of this relation, we get B related to A. Thus, A related to B implies B related to A. So, R is symmetry. Now, the third property is transitive. Now, in transitivity, we assume that A related to B and B related to C. So, by definition of relation, we get A is congruent to B modulo N and B is congruent to C modulo N. So, by definition of congruence, N divides A minus B and N divides B minus C. So by definition of divisibility, A minus B equal to N into K1 and B minus C is equal to N into K2 for some K1, K2 belonging to Z. Now adding these two equations, we get A minus C is equal to A minus B plus B minus C, which is NK1 plus NK2. That means A minus C is equal to N into K1 plus K2, where K1 plus K2 is an integer. So by definition of divisibility, N divides A minus C. So by definition of congruence, A is congruent to C modulo N. So by definition of relation, A is related to C. So R is transitive. So we have shown that R is reflexive, symmetric and transitive. Hence, it is an equivalence relation on Z. Now the next part is to decide equivalence classes. So for any element A, by definition equivalence class of A is X in Z such that X is related to A. Now we simplify it further. So X related to A means X is congruent to A modulo N. It means it contains X in Z such that N divides X minus A by definition of congruence. It means it is X in Z such that X minus A is Nk for some K belonging to Z by definition of divisibility. Therefore, equivalence class of A contains X in Z such that X is A plus Nk for some K in Z. Thus, equivalence class of A is equal to A plus Nk, K belonging to Z. So, this is the general equivalence class of A for any A belonging to Z. Now, by taking particular values of N, we can find the equivalence classes. So, if I consider N is equal to 7 here, Then equivalence class of A will be A plus 7k, where k is an integer. Again, by taking particular values of A, we can find equivalence class of every element of Z. For example, if I take A equal to 1 here, then equivalence class of 1 will be 1 plus 7k, k in Z. Now as k is varying over set of integers, take k equal to 0, 1, 2, 3 and so on, minus 1, minus 2, minus 3 and so on. So for k is 0, this will be 1 plus 7 into 0, which is 1. For k is 1, it is 1 plus 7 into 1, which is 8. Similar way, for k is equal to minus 1, 1 plus 7 into minus 1, which is 1 minus 7 equal to minus 6. So in this way we get equivalence class of 1. Similar way you can put a is 2, a is 3, a is minus 1, minus 2 and so on. Now equivalence class of A equal to x in Z such that x is congruent to A modulo n. It's called as the congruence class of A modulo n. This is also called as residue class of A modulo n. Now see what is the meaning of partition. So partition is nothing but actually division into parts. Now in mathematics, see what is the meaning of partition of a set. So a partition of a set A is a collection of non-empty disjoint subsets of A whose union is A. Or for any set A, subsets AI of A is a partition of set A if first is A equal to A1 union A2 union AN. Secondly, AI intersection AJ is phi for any I not equal to J, means distinct subsets are disjoint, and third is AI is non-empty for any I. See, what is the meaning of partition of set A? So we are dividing the set A into its non-empty subsets whose union is completely A, and if you consider any two different subsets of A, then no element is common. So such type of collection of subsets of A is called as the partition of that set A. Now see this example. Suppose this is the set A. So here we are dividing A into 5 subsets. This is A1, A2, A3, A4 and A5. Now each is a non-empty set. Then A1 union A2 union A3 union A4 union A5 is equal to A. And if you consider any two distinct subsets of A like A1 A2, A1 A3, A2 A3, A2 A4, then no element is common. So such a collection is known as partition of that set. Now see this set A is equal to 1, 2, 3, 4, 5, 6, 7, 8. Now, if you consider the sets 1, 2, 3, 4, 5, 6, 8, 7. Now, all these 4 are subsets of A. All are non-empty. Then union of 1, 2, 3, singleton 4, 5, 6, 8, singleton 7 is nothing but 1, 2, 3, 4, 5, 6, 7, 8 means entire set A. Then see, there is nothing common in these two sets. Similarly, if you consider 1, 2, 3 and 5, 6, 8, their intersection is an empty set. 1, 2, 3, 7, again intersection is empty. 4, 5, 6, 8, intersection is empty. 4, 7, intersection is empty. And 5, 6, 8 together with singleton 7, again it is empty. Means they are pairwise disjoint. Their union is A and all are non-empty. Hence, this collection forms a partition of set A. Now, there is another partition, say first if I consider 1, 2, 3, 4 and another set is suppose 5, 6, 7, 8. Then again both are non-empty subsets of A which are disjoint and their union is A. So in this way for the given set A you can define many such partitions. For a set of integers, singleton 0, then positive integer or natural number set and negative integers. These three sets constitutes a partition of Z. Now, see, this is one important theorem regarding equivalence classes. The equivalence classes of an equivalence relation on a set A constitute a partition of A. Conversely, for any partition P of A, there is an equivalence relation on A whose equivalence classes are the elements of P. So, if you consider any equivalence relation on set A, then the corresponding equivalence are pairwise disjoint, they are non-empty, and their union is A. So they constitute a partition of A. In reverse way, if there is some partition P of A, then for that partition, one equivalence relation is associated with it, whose equivalence classes are the elements of B. Now, next example is find all congruence classes of Z modulo 4. Now already we have seen the definition of congruence classes of Z modulo n. Now we consider x as any integer. Now if we divide x by 4, then the possible values of remainders are 0, 1, 2, 3. So for these values only we decide the congruence classes or equivalence classes, because for remaining elements we get identical equivalence classes. Now to find a congruence class corresponding to 0, by previous part, congruence class of 0, which is 0 bar, is equal to x in z such that x is congruent to 0 modulo 4. That means 4 divides x. So x is equal to 0 plus 4k, where k is an integer. So for k is 0, 1, 2, 3 and so on, the set contains 0, 4, 8, 12 and so on, minus 4, minus 8 and so on. So this is the congruence class corresponding to 0. Similarly, for congruence class corresponding to 1, it is x in z such that x is congruent to 1 modulo 4, means 4 divides x minus 1. So x is 1 plus 4k. Again, by taking the different values of k as an integer, we get this as congruence class corresponding to 1. Similarly, we can find 2 and for 3. If you consider again for next number, that is 4, then we get it as same as 0. Again for 5, same as 1. For 6, same as 2, like that. So the residue classes so form partition the set of integers. See, if you consider union of 0, 1, union of 0 with congruence class corresponding to 1 together with 2 and 3, then union of these four sets is equal to entire set Z. Then all these four sets are non-empty. And if you consider distinct congruence classes, then they are disjoint. So for these two sets, no element is common. Again for first, third, nothing is common. Same way for first, fourth, second, third, second, fourth and third, fourth. So they are pairwise disjoint, and hence these residue classes form a partition. Now similar to this, for modulo 4, for any natural number n, the set of congruence classes, that is residue classes modulo n, is denoted by Zn, and it contains the elements 0 bar, 1 bar, 2 bar and so on, n minus 1 bar. Similar to previous example, here we have to find all congruence classes of Z modulo 6. As it is modulo 6, see what are the remainders. When you divide an integer by 6, the possible values of remainders are 0, 1, 2, 3, 4, 5. So it is enough to find the congruence classes for 0, 1, 2, 3, 4 and 5. Now see, to find congruence class corresponding to 0, again similar to previous example, it is x in z such that x is congruent to 0 modulo 6. It means 6 divides x minus 0. So x is equal to 6 into k. So by taking different values to k, we get congruence class is equal to 0, 6, 12, minus 6, minus 12 and so on. Similarly, we can find congruence class corresponding to 1, 2, 3, 4 and 5. So finally, this is the set of congruence classes modulo 6, which is 0 bar, 1 bar, 2 bar, 3 bar, 4 bar, 5 bar. So this is the end of unit 1.